We finish with a crucial property satisfied only by Poisson processes, the pasta property. Consider the evolution of the number of customers in the queue n of t when time goes by. Look at the time intervals n of t is equal to, say, a value I. In the picture, these intervals are of length t1, t2, t3, etc. The ergodic theorem says that for a continuous time Markov chain with stationary probability pi, the percentage of time in state I approaches pi I as the observation time tends to infinity. This means that t1 plus t2 plus t3, etc., divided by t, the observation time, tends to pi I when t goes to infinity. This is called the ergodic theorem. For instance, for the MM1Q, pi I equals rho to the I times 1 minus rho. What is called idle time corresponds to the period of time during which the system is empty. The ergodic theorem said that asymptotically the idle time is almost equal to pi 0, that is to say 1 minus rho. Having seen the ergodic theorem, a new problem arises for queuing analysts. The blocking probability is the probability at steady state that the system is full and therefore can't accept any further customers. According to the ergodic theorem, this probability is equal to the percentage of time during which the system is blocked. On the other hand, what really interests the practitioners is the loss probability, the probability that a customer finds the system blocked upon his or her arrival. These two probabilities have no reason to coincide in general. Consider, for instance, the DD11Q. The inter-arrival and service times are deterministic. There is one server and no buffer. We choose the time unit that corresponds to the inter-arrival time. The service duration is rho, which is assumed to be less than 1. The time during which the system is blocked corresponds to the orange part of the picture. So, the percentage of time the system is blocked corresponds to the percentage of the orange area, which is equal to rho. If we follow the previous definitions, this means that the blocking probability is equal to rho. On the other hand, at each arrival the system is empty, so the loss probability is 0. So, there is a priori no relationship between blocking and loss probability. However, there may be such a relationship, and this property is known as the pasta property. Pasta is the acronym for Poisson arrivals seed time averages. Or in other words, if the arrivals in a system occur according to a Poisson process, then the blocking and loss probabilities do coincide. For a queue represented by a continuous time Markov chain, the blocking probability can be computed from the stationary distribution. So we have a way to really find the quantity which interests the practitioners, namely the loss probability. Let's have a look at the finite capacity MM1Q, namely the MM1KQ, meaning that the buffer has a finite capacity of size k-1. The practitioner's goal is to find the right value of k. If it's too big, it will maybe cost too much. But if it's too small, there will be a huge loss probability, meaning bad quality of service and thus unhappy customers. The quality of service is measured here by the loss probability. So, knowing the load rho, the problem is to find k such that the loss probability is less than the desired threshold. The transition diagram is a truncation to 0k of the MM1 diagram. It is a birth-death process, so we can apply the results we saw before. the local balance equations should be satisfied. Mu pi 1 equals lambda pi 0, mu pi 2 equals lambda pi 1, and so on and so forth, until mu pi k equals lambda pi k minus 1. Then the stationary distribution of state I turns out to be proportional to rho to the I. Using the normalization condition and the formula for the sum of a geometric series, we get pi I equals rho to the I times 1 minus rho divided by 1 minus rho to the k plus 1. We have one blocking state which corresponds to a full system, meaning that the number of customers is equal to k. And since the arrivals are Poisson, the loss probability is equal to pi k. We can plot this loss probability for k fixed against rho. It is more meaningful to represent it in a semi-log scale since the values are fortunately rather small. 3 observations are worth mentioning. Doubling the size of the buffer does much more than dividing the loss probability by 2. For instance, for rho equals 0.5, the loss probability for k equals 10 is almost 2 orders of magnitude less than the loss probability for k equals 5. In practice, this is very convenient since it means that adding a few resources may drastically improve the performance of the system. On the other hand, doubling the load for a fixed capacity does much more damage than doubling the loss probability. For instance, for k equals 5, there is more than 1 order of magnitude between the loss probability for rho equals 0.5 and the loss probability for rho equals 1. The third remark is that mathematically speaking, the system is always stable since we have a finite state space. However, as rho gets bigger, the loss probability tends to 1. Of course, the bigger k is, the bigger rho has to be in order to reach a given threshold of loss probability, but inevitably it goes to 1. The last plot is the evolution of k, which guarantees the loss probability to be less than 0.001, a rather severe requirement when rho varies. Once again, it's important to notice the nonlinearity of k. For low loads, k varies slowly, whereas for higher traffic, the variations are considerable and the values soon become very high.